Have you ever really thought about what makes your fleece jacket so soft, but a climbing rope strong enough to literally save your life? What gives all these different materials their own unique superpowers? Well, the answer to all of this is a secret, and it's hidden at a scale our eyes can't even see.
Right. So the key to everything, from the stretch in your favorite pair of jeans to the insane strength of a carbon fiber bike frame, it's not magic. It's engineering. But this is engineering on a molecular level. So, what is the secret hiding inside the very threads of our world?
You got it. The answer is its invisible architecture. Every single property of a fiber, how strong it is, how it feels, whether it soaks up water, it's all dictated by the way billions of tiny chain-like molecules are arranged, packed, and held together. So today, we're going to become molecular detectives, and we're going to uncover that architecture.
So before we can start investigating, we need to know what we're looking for, right? What does it even take for some material to be a fiber in the first place? Well, it turns out there's a very specific blueprint it has to follow.
Think of it kind of like a recipe, and it has 4 essential rules. First, you need these long, straight molecules called polymers. Second, you have to get those chains lined up so they're mostly parallel, like a brand new box of spaghetti. Third, you need some kind of attraction, a force, between the chains to hold the whole thing together. And finally, you need just a little bit of wiggle room, some freedom for them to move, so the fiber can have a bit of stretch.
Okay, so how do scientists actually see this hidden world? We can't just bust out a normal microscope. Nope. We need a set of high-tech tools, our investigator's toolkit, to peek inside the fiber and map out its molecular crime scene.
So, our investigation is going to rely on 3 key tools. We're going to use X-ray diffraction to see the structure, an electron microscope to get a really nice close-up, and infrared radiation to figure out its chemical identity. Each one of these tools reveals a different, absolutely crucial piece of the puzzle.
All right, we've got our blueprint, we've got our toolkit. It is time to put on our lab coats and start decoding these molecular clues. Let's see what these powerful instruments can really tell us.
First up is X-ray diffraction. This is our go-to tool for figuring out the physical arrangement of all those molecules. It's how we find out if the fiber's internal structure is all messy and chaotic, or if it's neat and orderly.
So here's how it works. We fire a beam of X-rays at the fiber. And as you can see in this diagram, if the atoms inside are arranged in these nice, neat, orderly layers, what scientists call a crystalline structure, the X-rays will bounce off or diffract at very specific, predictable angles.
Now this is where the real detective work comes in. By measuring that angle of reflection, we can plug it into a formula called Bragg's law to calculate d, and that's the exact distance between those atomic layers. That distance, that number, is our crucial clue. It tells us how tightly packed and orderly the molecules are, which is a measure of the fiber's crystallinity, basically how organized it is on the inside.
Next up in our toolkit is the electron microscope. Now, if X-rays give us the internal floor plan, you can think of this as our super-powered camera for taking incredibly detailed photographs of the fiber's surface and its overall shape.
It works a bit like a regular microscope, but instead of light, it uses a beam of electrons. You can see them starting from the source at the top. Magnetic fields then act like lenses to focus that beam, creating a ridiculously magnified image on a screen. This gives us direct visual proof of the fiber's shape. It's pretty amazing.
Okay, our final tool is completely different from the others. Infrared absorption doesn't tell us about the physical arrangement, it tells us about the chemical makeup. It's literally like taking a chemical fingerprint of the material to identify exactly what it's made of.
What you're looking at right here, this is the infrared spectrum for nylon. To get this, we shine infrared light through the material. Certain chemical bonds inside the nylon molecule start to vibrate, and they absorb that light's energy, but only at specific frequencies. The machine plots all this out, and it creates this unique pattern of peaks and valleys, literally nylon's chemical fingerprint. No other material will have this exact same print.
And here's the cool part. We can read this fingerprint. Each one of those peaks corresponds to a specific type of chemical bond. So, for example, that big peak around 3305, that tells us there's a bond between nitrogen and hydrogen. The one at 1640, that's the signature of a carbon-oxygen double bond. By matching these peaks to known values, we can identify all the building blocks and confirm that, yep, we are definitely looking at nylon.
So let's just put these last 2 puzzle pieces together. The infrared method tells us what it is, the chemical identity of the fiber. X-ray diffraction tells us how it's built, its physical structure.
And, really important, infrared analyzes all the molecules, messy or not. But X-ray only sees the neat crystalline parts. You absolutely need both to get the full picture.
Okay, so we've gathered our evidence. We know how to figure out a fiber's chemical makeup and its physical structure. So now for the payoff. How does all this hidden architecture translate into the real-world properties, the superpowers that we can actually see and feel?
Let's start with a really practical question. Let's say you're an engineer, and your job is to design a stronger fiber for, I don't know, a rope, or maybe a bulletproof vest. What parts of that molecular architecture would you need to tweak?
Well, our investigation gives us the blueprint. To make a fiber stronger, you need to do 3 things. First, use longer polymer chains. That's called increasing the molecular weight. Second, you want to increase the crystallinity, which just means you pack those chains together in a more orderly, rigid structure. And third, you improve the orientation, making sure all those chains are pointing in the same direction, all working together like a team.
But what if strength isn't what you're after? What if you're designing athletic wear and you need more stretch? Or maybe you're making a towel and you need it to be way more absorbent? This, my friends, is where the engineering trade-offs come in.
See, to get more stretch, you actually have to do the opposite of what you do for strength. You need less crystallinity and less orientation to give those molecular chains room to move and uncoil. And for more absorbency, you need more chemical groups that attract water, and again, less crystallinity, so water molecules have space to actually get inside the structure. It's a balancing act.
And that really brings us to the single most important takeaway from all of this. The structure defines the property. If you want to change the material, you have to first change the architecture. It's the ultimate blueprint for everything.
So, we've cracked the code that governs the materials we use every single day. The only question left is, now that we know the rules, what incredible new materials are we going to design tomorrow?